In this video, we'll be using the elimination method to solve systems of 3 or more variables. I'm just going to do examples of 3 variables, but you could use the same idea to solve systems of any number of variables, assuming they have the right setup. But we're not going to be worrying too much about the mathematical theory and focusing mostly on the method for what real problems tend to look like. And that being said, there were a few examples in our packet where where I looked at examples where the system could have no solutions and infinite solutions and what those look like. But I'm going to skip those in this video because real problems should not have those as possibilities. And while you probably have seen them in algebra before, they're not really that relevant to us here in business math. So, and I'm not going to test you on them, so I wouldn't really worry about that. But you can go ahead and practice on those and see what will happen to a system that has infinite or no solutions. But let's focus on systems with 3 variables. And like before, a system of 3 variables just means that instead of having x and y equal to something, we now have 3 different unknowns in a more complex system. And so in a real problem, we won't necessarily just have like a system of equations with both just x and y would be indicative of a scenario where y and x are directly related. Like in life, a lot of times you have, well, if something happens, we can do some math to figure out, well, what would be the resulting value. Like say I know my costs. I have a fixed cost of this much and a variable cost of this much, and my total cost is related to those. But sometimes you have more than one cost. You have this cost, a second cost, a third cost, and that all adds up to something else. That just presents with a more complex mathematical equation where you have a lot of different possibilities. And the more different possibilities you have, the larger the equation. Again, we're assuming it's linear. But in this case, let's just say we have 3 equations with 3 unknowns. Let's say that x plus y plus z is equal to -2, x plus 2y minus 3z equal 12, and 2x minus 2y plus z equal -9. And our goal here is to figure out what is x, what is y, what is z that will simultaneously work in all 3, which is a very similar process to what we were just doing. It is just a little bit more difficult because we have 3 different things. And the solution should work in all 3 as well. So say, for example, if I want to know, is this ordered triple a solution, I would need to plug it into all 3 to make sure. Like I could try plugging in 0, -1, -1. If I plug it into the first equation, that would give me 0, -1, -1 equal -2. And that makes sense. But as I said, it needs to work in all of them. So I could try it in the second equation, which would be 0 minus 2 plus 3 equal 12. That's definitely not going to make any sense. So that first ordered triple is not a solution to the system as a whole. We could check the next one to see 5 minus 3 minus 4 equal -2. Now that makes sense in the first equation. In the second equation, I would have 5 minus 6 plus 12 equal 12. That's not going to make sense, so this one's not going to work. But what you can see is that if I was trying to guess a solution, which is a lot of times how people will try to solve problems, is if they don't really know the process, they'll just kind of say, well, maybe this is the answer, maybe this is the answer, and kind of guess their way to finding it, which is technically possible. I don't know what I just did. I zoomed way far in on my tablet. My point was that the guess and check method is much harder for these, and we instead of trying to do it that way, algebra is going to save us a whole lot of time if we know how to do it. And then we could check the third one out just to see. Let's go ahead and check it. I don't actually remember if it works or not, but the only way to know is to test it. So if I plug it in the first equation, -2 plus 1 minus 3 equal -2. No. So actually that one's not going to work either. So anyways, what is the answer? I don't know. I didn't give a proper option, but the only way we could find it is to make sure it works in all, which none of these do. So how do we solve it? We typically will use elimination. So let's look at a few examples and actually solve them via elimination. And the strategy for elimination becomes a little bit harder with multiple systems because instead of just having two equations that we're going to add together, we want to add all three equations together in the same way. But instead of trying to think about adding all three equations together at once, because that's not necessarily going to work the way we want it to, the general strategy is to start with two equations, add them together, eliminate one of the variables, and then take a different pair and eliminate that same variable from the new pair. So let's say if I'm looking at the first two equations in this example, and a lot of times I might number them just to help when we're referring back to them later. I'm going to add equation 1 and equation 2 together. And I'll do that over here, I guess. X plus y minus z is equal to minus 1 and 2x minus y. And the reason I would choose to add these together is because notice that in both equations I have y and minus y. So those two equations were ready to eliminate from the beginning, which is very nice because that's the goal, is always to eliminate my variables. Because as I eliminate my variables, I'm simplifying and making my equations easier to solve by removing the unknowns. And what I do is I get a new equation. I'm going to go ahead and call this equation 4 because it's not solved yet because I've only eliminated one variable, but the goal is to eliminate two of the variables to get x, because once we get one unknown by itself, then I could reverse the substitution and find y and z. Or, I could solve for whatever variable I want. I'm choosing to eliminate y because it's easy. But notice in this equation 4, since I have two unknowns still, my goal is to find another equation that's similar to this using both x and z so that I can add that to an equation and form an elimination. But that's all kind of, it's kind of hard to explain that in a very simple way. But basically what you want to remember is you want to do exactly what I just did twice. I want to eliminate y with one pair. I want to then find a different pair of equations and eliminate y from that. So what I'm going to do next is I'm going to use equations 2 and 3 and eliminate and do the exact same thing, eliminate y from those as well. So I'm just going to copy them down over here. Equation 2 is 2x minus y plus 2z equal minus 1. And equation 3 equal to minus 9. And I'm going to go ahead and label my equations as well, just so that I can, it's easier to follow later. You don't have to do this, and I definitely don't do this when I'm actually solving them, but when I'm teaching, it helps to keep some organization to my problems. But the issue with equations 2 and 3 is these are not ready to eliminate. And also, you always want to eliminate the same variable twice. I don't want to say I could have tried to eliminate x here. If I eliminate x, it's not going to help. And we'll see why in a second. But I want to eliminate the same variable in two different pairs. So I want to make sure I eliminate y here. Since it's not ready to eliminate, what I want to do is make sure to match the coefficient. And if I just multiply through equation 2 by 2, that would give me 4x, 2y, 4z, and negative 2. So that's a little bit sloppy. Let me do that a little bit better. So this would become 4, this would become 2, this would become 4, and this would become negative 2. But basically, I'm multiplying the whole equation through by 2 so that it is now ready to eliminate y. And now I can add them together, do the elimination. So that would be 4 minus 3 is x, 1x. 2 minus 2 eliminates, and 4 plus 1 is 5z. And negative 2 plus negative 9 is negative 11. And this gives me a new equation where z has been eliminated. And assuming I use two different pairs of equations and I eliminated the same variables, what I should get is two new equations. Notice equations 4 and 5. And in both of these equations, notice how they're the same. They're very similar. They're both now down to two variables, and they're both the same. It's 3x plus z equal minus 2, and x plus 5z equal minus 11. Now I could take those two equations, eliminate the variable of my choosing to finish the elimination. So my next step would be to take equation 4 and 5 and perform elimination on these new sets of equations. And in its initial uh, setup, it's not ready for elimination because neither variable is paired. But if I multiply through the second equation by -3, that will match them all up because this would give me -3x, this one would give me -15, and this one would give me 33 in positive because I multiplied through by a negative. That is ugly, but I'm just going to leave it. Okay, and now this pair of equations is ready to eliminate. Now I could add them together. 3x minus 3x will be 0 or cancel. Z minus 14z would be z minus 15z would be -14z, and -2 plus 33 would make 31. And what I would get here is z is equal to -31 over 14, which would be part of my answer. And it appears as though, and as I said, sometimes the answers to our systems will not be pretty. And most of the time in the homework, they're going to make them so that you're not going to get these horrible fractional answers. But sometimes that's how life is. Sometimes the answers are not nice whole numbers. And even though I see a fraction, my initial thought might be, did I do something wrong? But this example, I did this on purpose because sometimes it will happen. Also, I'm not quite done because I also need to find x and y, because just like before, the goal is to find an order triple x comma y comma z that will work in all three of them. I found the z, but I need to back substitute to find x and y. And the way we do this is, or how I recommend doing it, is by reversing the sub by taking z, plugging it back into your equations 4 and 5. Because notice in these equations, these are simpler because they just only use x and z. Say, for example, I plug it into 4. Z would go right there. I could solve x pretty easily by just adding it to the other side. So let's do that. So if I were now to plug that into equation 4, this would give me 3x plus z is equal to -2. And I could find x by adding 31 over 14 to both sides. So -2 plus 31 over 14. And -2 would be, if I match the denominator, 28 over 14. So 31 minus 28 is 3 over 14. And then it looks like I should have given you guys more room on the packet here. I'm just writing very big because I could write smaller. It's just the way my tablet's set up. And then I need to divide by 3 from both sides, which would give me x is equal to 1 over 14. Basically, I could then find x. And now that I know z and x, I could reverse it again, plug it into one of the 3 original equations to then find y. So the general flow is we're going to add all the equations together to eliminate in that same way. Then we're going to work our way back. So once I have z, I plug it back into 4 or 5. Once I have x, I plug it back into 1, 2, or 3. So now plugging both of those into, I'm going to use equation 1 because it's the lesser of 2 evils here, or of 3 evils, I mean. And equation 1 said that x plus y minus z is equal to -1. And you might be wondering right now or thinking, is there a way I can do this in my calculator? The answer is yes, but we're not gonna get to that till chapter 6. Because using the graphical method, calculators which can graph in 3D could use a graphical way of solving, and there actually is such a thing called an equation solver, which some calculators have too. But we're going to wait till we get into chapter 6 to talk about how that works. But anyways, I know x is 1 over 14. I don't know y still, and I know z is 31 over 14. Since it's negative z, it would be a double negative. And that all should be minus 1 if equation 1 is to be believed. But now, basically, I have y. I could combine the two fractions. 32 over 14 is equal to minus 1. And then I could subtract the 32 over 14 from both sides. And to now add those two things together, 1 would be equal to 14 over 14 with the common denominator. So I would have negative 14 minus 32, which should be negative 46 over 14, assuming I did not mess up my math. And as a last step, because now I've done all this math to find x, y, and z, I'm praying that I didn't mess up, that this actually works. And what I advise doing is, again, to check, we would need to check in all of our equations to make sure. But since I used equations 1 and 4 to do this, I'd recommend probably using one of the other equations to check, maybe 2 or 3, just to make sure it actually works in all of them. So let's go ahead and take my answer and plug it into equation 2 to make sure. And we could always just do this with our calculator. So since equation 2 is 2 times x, well, what I claim is that x is 1 over 14. And then minus y, which I claim is negative 46 divided by 14. And that plus 2z, which I claimed was negative 31 over 14, is supposedly all equal to negative. And when I do all that, I did get negative 1. So I know I'm good. I did it right. And again, I could double check the other equations. But at this point, if you're very confident in your algebraic ability to solve these, like I've taught this many times in my life, so this is something I could do in my sleep. It's something that, you know, I would check it, because these problems, there was a lot of steps, and the more and more steps I do, the more likely I am to actually mess it up. Regardless of how good or bad you are at math, always suggest checking your answer. And I could check them in all of them, but I think that that's probably not worth our time here.